Well, in this video, I will solve the separable differential equation, and I'll show you how to use Mathematica to supplement your work, as well as to use Mathematica to solve the initial value problem entirely. So let's work on the left side over here, first of all, trying to solve this primarily by hand, and then we'll use Mathematica as a kind of assistant. So as you can see, we have an expression in y and this expression in x, and we want to separate, putting all the expressions involving y on one hand and on the left side, for example, and then all the expressions involving x on the right side. So we can start by dividing both sides by cosine of x, for example. Okay. Um, and we'll obtain, it looks like we can also divide e to the y, right, by e to the y. So that way we'll just move the y expression to the left side. So we have e to the 2y minus y here, and then dy. And we can also multiply both sides by dx, of course. So that way we'll have sine of 2x over cosine x dx. So I think the separation is ready, and we can start integrating both sides here. I see, I forgot the e to the y on the left side. I see. So to integrate the right side, it would help to remember the double angle identity for sine. So we could rewrite that as 2 sine x cosine x. And so that way we'll have cosine canceling out. On the left side, we could rewrite this as e to the y minus y e to the negative y. And integrating this should be done using integration by parts. Now, at this point, I would recommend using Mathematica, right? So even if you forgot the double angle identity, it wouldn't be a problem. So I would just use integrate feature. So I'm going to go ahead and type integrate, and then in brackets I will put the expression. So we'll start with e to the y. Okay, so that's the left side expression. Now, even though y is a function of x, I don't want to indicate that. I'm just going to leave it as y there. And then I just need to specify that I'm integrating with respect to y. So that's what this comma y means. It means I'm integrating with respect to y. So it's like this dy over here. And then capital E, of course, represents the Euler constant E. So that should be it. Okay, so that's the result of integration. You could try to get that expanded. So in case you don't know this, %1 refers to the output of line 1. So just it's the first output. So it's whatever is outputted here is stored in the variable that can be accessed by typing %1. So anyway, so this is the expression that represents the antiderivative of this left side here. You can copy it, so you can also convert it to an image or download it as PNG. Just going to try to see if I can copy here. Maybe this wasn't the best decision after all. I could have just scribbled that instead. All right, so that's the left side over here. As far as the right side, this should be easy. but you would use the similar method to integrate. So we should, of course, obtain -2 cosine -2 cosine of x. Okay, and then of course we have this arbitrary constant. All right, so this pretty much completes the implicit solution, right? So we have e to the -y plus e to the y plus y e to the -y is equal to -2 cosine of x plus a constant. So this is a family of curves, of course, in case you don't know this. So it's actually infinitely many possible curves, and we could graph this if we wanted to using contour plot. You can also graph this in Desmos. Of course, you can try to introduce the C as a slider. But the question is, how would we at this point solve for C? Well, we go back to the initial condition, y of 0 is 0. So what that means is when x is 0, so when x is 0, y is going to be 0. Basically, that's what that means. So all we need to do is plug in 0 in for this expression, okay? And for x's as well as for y, and see what the resulting expression is. We can also do this with Mathematica. So let me try and typing that in. So we have e to the well, let me go back to this expression here. Okay, that's the first output, right? So I can just let it equal -2 cosine of x plus this arbitrary constant, which you want to use lowercase c in this case, not capital, because that's a protected value. So notice this is the same equation as the one here, okay? And so all we need to do is plug in 0 for x and 0 for y. So the way you do that is you say, you can type that here, by the way. You could just do /, let me just do that down here instead. So we could just do %3, again, refers to this equation, okay? And so you could just say / dot, and then in curly braces, you specify the plugins, right? So you plug in 0 for y and 0 for x. The way you do these arrows, by the way, is you just do a dash and then the larger than symbol, okay? So a regular dash, which is next to the, basically it's the subtraction sign, and then the larger than symbol. And then if you put it next to each other, it just turns into an arrow, okay? So now Mathematica, and by the way, this / dot, what that means is plug it in, right? So it just means evaluate or plug in, and then you specify the plugins in curly braces. Now, so it has plugged it in, and we have this equation, and this is obviously an easy equation. You can see C equals 4. But in case this was complicated equation and you need Mathematica to solve it for you, you can even have that done. So you just type solve, okay, and then you enter the equation. In this case, it's the fourth output, is this equation. And then you specify the value you want to solve for, which is C. And then it solves for you, okay, C is 4. So basically, we applied this initial condition, and we were able to obtain that C is equal to 4 indeed. So we can come back here and rewrite the same equation. So again, in implicit form, e to the -y plus e to the y plus y e to the -y is equal to negative cosine of x plus, this time we can now happily put 4 instead of C. And so now we have a particular solution, a specific solution given the initial condition. All right, so that pretty much concludes the kind of the by hand, or at least partially by hand methodology, right? Of course, over here we had to technically use integration by parts, but we kind of skipped that over, kind of a calculus 2 skill, which we use Mathematica for. Now, could we have used Mathematica to kind of skip all of this and get to the final solution? And the answer is yes. I mean, depends on what your goal is. I mean, I always recommend doing things by hand as much as you can. But I do want to give you the opportunity to try this as well, perhaps as at least a way to check your answer. So what we need to do at this point is we need to use DSolve. So DSolve is a differential equation solver. And again, everything you put, it has to be in brackets. And notice the D and the S are capitalized. That's absolutely important. You can't use the lowercase. If you do, then it will not work. It'll treat this as a variable. Now we need to enter this equation. Okay. Now we can't just enter either the 2y. We have to be careful because you have to understand that this y over here, right? This is actually a function of x. And we know that because we have the dy dx here, right? And we also have the independent variable. So y here is the dependent variable and it depends on x. So that's actually a function. So over here, what we need to do is enter it as a function. So we're going to say e raised to the 2 times y of x, okay? Minus y of x. We can't just enter minus y. So we need to put that in parentheses. Okay. And to just to be safe, I'm going to put this also in parentheses to indicate that 2y of x is indeed the entire exponent of e. Now we're going to multiply by cosine of x. Again, cosine has to be capitalized. Okay. And then dy dx, the way you enter it is you just enter y prime of x. Okay. So that's what dy dx is. All right. And then we have double equal signs always, and then e to the y of x. Okay, whenever you're doing equations, you need to use double equal signs times sine of 2x. Again, notice the sign is capitalized. Okay, so far all I've done is I've pretty much entered the equation. Okay, so that's all I've done. And by the way, what I could have done is instead of using DSolve and putting in all this in, I just did Control X. What I could have done is I could have said equation equals, and then I could have defined the EQ variable, standing for equation, as this giant equation, right? And then now if I enter EQ, it knows what EQ is. It's this equation, all right? And so now when I want to solve this, I could just say DSolve, and then I can just type EQ. I don't need to type the whole equation. So I want to solve for this equation. I want to solve this equation for y of x, and then the independent variable is x. So I need to enter 2 more parameters here. I need to enter the equation. I need to enter the dependent variable, the function I'm looking for actually, and then the independent variable x. Okay, and so here we go. Here's the answer. Now, of course, the question is, what in the world does this mean? All right, so first of all, these hashtags, they are basically placeholders for the independent variable. You can think of it like X, basically, right? However, in this particular context, they're not going to represent X. They're actually going to represent Y, because what's going on is this expression is saying that you have the inverse of this expression, with this expression, C1 minus 2 cosine of x, plugged in. Okay, so what that means is that e to the y, if you were to replace this hashtag ones with y, right, and set it equal to this expression, you would get what we're looking for. Okay, so I mean, it's similar to what's going on here, right? So over here, we wish we could solve for y here, but we can't. Unfortunately, we can't solve for y. There's this is not possible. But if we could solve for y, right? If we could solve for y, it would be like it would be like finding the inverse of this expression. Okay. And the fact that this is equal to negative 2 cosine of x plus 4 means that the inverse of this, if this was with respect to x, the inverse of this with this plugged in would have been the expression we're looking for. So it's hopefully that made sense, but it's confusing the first time you see it for sure. So effectively, these two are the same answers. Hopefully you realize. I'm just going to copy this so I could kind of replace things. But by the way, this ampersand symbol is just saying that it's just a marker to show the end of the function expression. So this is a function expression with hashtag, and this is a marker for the end of a function expression. So just to show you how we can define functions. So in Mathematica, we can say f of x, okay, is equal to, let's say, x squared, right? So this is one of the ways you can define a function, and you can just say f of 2 is, of course, 4, right? So that's one way. Another way is you can say f is the function, and then you specify of x, and then you specify the function. So this is another way you could define a function, okay? So this does the same thing, and you could, again, do f of, let's say, 3 this time, and of course you would get 9. A third way to define a function is to say f equals, and then you use hashtag. You just say hashtag squared. Then one more thing you need to do is enter the ampersand to state that you're done defining the function. It's like the end of the function, right? And so now you have this expression. All right. So again, you could do f of let's say f of 5, and again we get 25. So these are 3 different ways of defining a function in Mathematica. And once we define it, we can use it in any way we like, including within differential equations. All right, so back to this expression. I'm just going to copy this here, back here. All right, just to show you how this is indeed pretty much the same thing as what we got over here, actually. All right, so basically you have e, so you can replace this hashtag e to the hashtag with e to the y minus e to the negative y, and then you have -1 minus y, and then you're just going to put equal sign, and then we're going to have -2 cosine of x plus the constant. And notice it says C1. That's because in case there's a C2, there's going to be it's going to be labeled as such also. And this, hopefully, you realize this expression is really the same as this expression here. So they're the same. Now the question is, what about the constant, right? If we're going to use DSolve, how would we solve the constant? Well, you could do it the way we kind of already did it, right? But I think it's much better to just go back from the beginning and just say, you know what, I'm going to enter 2 equations. All right, and in order to do that, you need to enter this into curly braces. So the second equation is basically going to be our initial condition, right? Which was y of 0 equals 0. So we're going to just enter that here, y of 0 equals 0. So again, don't forget the double equal signs. And notice again, this equation is just this giant expression here representing the differential equation. And then let's do Shift Enter, and here we go. You can see the C1 is gone. It's been replaced with 4 automatically. Everything else is the same. So this is indicating the same solution as what we got over here. Okay, so they're the same thing. This is obviously a way to cheat, right? And not to do any work. But again, I urge you to, of course, do the work, and so that you can learn, so that you can actually learn how to do this by hand, and so you could also understand the process, of course, and of course to have it solidify in your mind. All right, that's pretty much it. Thank you for listening.